Independent events are events that have nothing to do with each other. And needless to say, it's a lot easier to work with them when because you don't have to figure out some weird interaction between two events that do have something to do with each other. Typical case where independent events come up is, for example, you toss a coin 5 times, and then you're about to toss a coin the 6th time. Is there any reason to think that what the coins did the first 5 times is going to have any influence on the flip of the 6th chord of the coin for the 6th time? Well, it's reasonable to assume not, which is to say that the outcome of the 6th toss is arguably independent of the outcome of all the previous tosses. Okay, let's look at a formal definition now in this short video of just what is the technical definition of independent events. So what we said is that they're independent if they have nothing to do with each other. What that means is that if I tell you that B happened, it doesn't have any effect on the probability of A. That is, the probability of A given that B happened doesn't change the probability of A at all. That's it. Now this is one definition. Maybe this is the more intuitive definition, but another definition that's equivalent and is standard is that two events are equivalent if the product of their probabilities is equal to the probability that they both happen. That is, the probability of their intersection. Now, definition 1 and definition 2 are trivial equivalent, just using the definition of conditional probability. And if you don't see that, this would be a moment to stop, get a pencil and paper, and write down the 3-line proof of the equivalence of these two equalities. In fact, the 3-line proof has this as the first line and that as the second line. So you could argue it's really just a middle line that you're adding. Okay. The definition 2 has the slight advantage that it always works, whereas definition 1 implicitly requires that the divisor, remember, probability of A given B is defined as the probability of the intersection divided by the probability B. It's only defined if the probability of B is positive, whereas the second definition always works, and we don't have to put a proviso in about the probability of B being non-zero. So that's the definition of independence. Looking at this definition, what you can see immediately is that it's completely symmetric in A and B. Since multiplication is commutative and intersection is commutative, which is A and which is B doesn't matter. And what that implies then is that A is independent of B if and only if B is independent of A. Now, another fact that holds is that if the probability of B happens to be 0, then vacuously B is independent of everything, even itself, which isn't important but is a small technicality that's worth remembering by that definition. Now, again, the intuitive idea that A and B have nothing to do with each other is that A is independent of B means that A is independent of whether or not B occurs. That is to say, if A is independent of B, it ought to be independent of the complement of B. And that's a lemma that's also easily proved. A is independent of B if and only if A is independent of the complement of B. It's a simple proof using the difference rule. And again, I encourage you to stop and with a piece of paper and pencil and convince yourself that that follows with a 1-line proof.